Very nice. Hello. Hello, everyone. I'm sure you've talked about glass a lot today. You've seen a lot of glass. So today I'm going to focus on broken glass. As I said, you've seen glass like this in bridges, in facades, in windows. You know how these look like, you know how they act, and you know they are safe to use. Now, it gets interesting once the glass isn't safe to use anymore, because it then breaks. And it breaks spontaneously, and it breaks into a lot of fragments. And there lies a big problem, because since until today we don't really know how these fragments are evolving. So we need very, very cost expensive and time expensive tests to validate glass and to make sure that it's safe before we actually build it. Here you see such a test where it obviously failed because the laminated safety glass here slipped from the supports on one side. So now the question arises, maybe we could swap that out, these experiments, by just doing it numerically. We're doing other things numerically, right? We're doing FEM, we're doing any kinds of work in the simulation kind of view. So here is what we're trying to do. We're trying to simulate, depending on certain boundary conditions, how the fracture pattern will actually look like. First of all, we therefore have to look at influences that are creating this or that fracture pattern. The most important one is the pre-stress level. When thermally heat treating glass, we get a stress gradient that's creating compressive zones at the surface and tensile zones in the center. Overall, the glass is still in equilibrium, obviously. On the right, you can see that different stress levels create vastly different fracture patterns. Today, I'm going to focus on the fracture patterns on the right, which is for fully toughened glass. First of all, you need a lot of data. Because we are dealing with fracture mechanics kind of stuff, we need very much data. So here you can see some experiments, or the experimental setup. We have a pointed punch with a weight attached to break the glass in a controlled way. Also, we're looking at different boundary conditions to see what influence might arise from that as well. And the first things you see that when looking at such a fracture pattern, you see that there's an impact point, the origin of the fracture, and some kind of pattern that arises around the fracture point, as you can see on the right side in a real-world scenario. So looking at this, I tried to model or to analyze the fracture patterns in terms of a distance to the impact position. When we do that, we can see that when we try to put an ellipse around each fragment, we get some kind of orientation towards the impact position. The left side of this slide shows that when increasing the distance to the impact position, we get different results in radial bands around the fracture origin. The same applies when we look at the fracture intensity, so the amount of fragments per square 50 millimeters. So that led me to make it like this and say that let's analyze these fracture patterns with regard to the distance to the impact position. The right side now shows these graphs that tell us how the orientation and the fracture intensity develop with increasing distance to the impact. We did that for now 130 specimen experiments, and we then placed the results with regard to the distance to the impact position on these graphs. You can easily see that, for example, in the middle, you have the two-sided support boundary condition, where you can see that with increasing strain energy that comes from the stress gradient from pre-stressing, we get a less and less deviance with regard to the distance of the impact position. Now, so far so good. Now we have the data, now we want to actually generate a fracture pattern, what this talk is about. So we start by randomly distributing points on a plane, that is our glass plate that we want to simulate, and it follows the fracture intensity. So we know how many points we need to generate, but we place them on the area randomly. We then apply a new approach that is placing geometries on top of each point. Now you can see that on the right it doesn't look like a fracture pattern at all, so there's one more step we need to do to actually generate a fracture pattern that looks somewhat realistic. We therefore apply the watershed algorithm that does the work for us and fills all the black spaces between the elliptic geometries we placed earlier with actual geometries. If we do that with each and every ellipse on our geometry, we can generate a fracture pattern that looks something like this. On the left, you see again the ellipses with dark spots around them that are filled by the watershed algorithm. And on the right, you can see a fracture pattern that looks pretty realistic. We can compare that optically with an actual fracture pattern seen here on the right, where we analyzed the individual fragment contours, and we can see that it looks pretty good already. But doing the comparison optically only is not very scientific, so we look at the overall fragment distribution. Here you can see on the x-axis the fragment base area, and on the y-axis the probability density of such base area. This graph shows us that the mean fragment area of the fracture pattern is modeled pretty nicely, and we also get smaller and bigger fragments that match the function of the experiment pretty well. That's it already from me. I hope you liked it, and if you have any further questions, you can contact me afterwards or scan these QR codes.